If I want to light a light bulb, I have to have two wires to connect to it because the current has to flow all the way through the device. Charges can flow in, charges have to flow out again. To connect it into a circuit, I have to use two wires. And actually, this right here is a plug which is stuck into a normal electric outlet. This wire right here is the hot wire. That's the one that's 120 volts. And I'm going to hook one wire up to that. And then if I turn on the outlet, what happens is nothing. Because the electricity has to have some place to go. When it flows through the bulb, it's going to go out someplace, and where it goes is back to the neutral wire, which is this one right here. So electricity connects back to the neutral wire. Okay? And if I turn this on, light bulb lights. Because now I have a complete circuit. Well, it turns out the neutral wire is also the same as the ground wire. And we can show this. This third wire over here is the electric ground, and it's actually connected to the earth. It is at 0 volts, which is the potential of the earth. So I'll take this wire, connect it up over here, and if I reconnect it, I get electrically, the ground wire works just as well as the neutral wire. Current goes through the light bulb, back to the ground. That's why the ground is used as a safety feature. Now this won't work if you have a ground fault interrupter outlet, but this one isn't, so it works just fine. It's the second connection to the ground. It's just like the neutral wire. Now, that makes a bit of a problem though. The fact that the neutral wire and the ground wire are actually connected to the ground, they're connected to the earth, can create a potential safety problem. Here's why. These two wires, the neutral wire and the ground wire, okay, these two wires are actually connected to the earth. My feet are connected to the earth. So if I touch either one of those wires, and let's just verify that everything's turned on and it's running. If I touch this wire, or if I touch this wire, there's no problem. That is at the same voltage as my feet. There's no potential difference across my body, no current. And as we know, it's current that you have to worry about. Here's the thing though. This wire is at 120 volts. My feet are at 0 volts because 0 volts is defined as the potential of the ground, and I'm standing on the ground. So if I grab this wire, there's a voltage across my body. Here's the thing though. I can do that. I can grab this wire and it's safe. Now don't try this. I have thought carefully about all the safety factors involved here. But you can see this light bulb is on. I can grab this wire, no ill effects. And here's why. My shoes. I'm wearing shoes with very thick rubber soles. They have an extremely high resistance. And there's a potential difference between me and the ground, but between me and the ground are very thick rubber soles of my shoes with extremely high resistance. As a consequence, vanishingly small current goes through me, and so I'm safe. And that's one of the reasons why I wear shoes like this when I'm teaching about electricity. And it's also why I keep my left hand in my pocket. Because if I keep my left hand in my pocket, I'm not going to get a potential difference between my hands, in which case my shoes with the thick soles aren't part of the circuit. So this, scary. I'm going to keep my left hand in my pocket. Then any potential differences between me and the ground, and any wire I touch is going to be okay. So my shoes provide electrical safety, just as do the shoes and boots worn by people who are apt to be working on high voltage power lines. And if you're working on high voltage power lines, you might touch one. And if you do, you might get a shock. To be sure that you don't, you have to wear special footwear. And our problem today corresponds to exactly that type of situation. Let's take a look. Here's our problem. A pair of boots designed to be worn by people working with high voltage electricity is designed to have a maximum current of 5 milliamps when there's a potential difference across the sole of 5 kilovolts. If a worker wearing these boots is outside standing on wet ground and touches a 1,000 volt live wire with one wet hand, will he be okay? Well, as always, let's extract the important information from the problem. The soles of the boots will pass a maximum current of 5 milliamps when there's a potential difference across the sole of 5 kilovolts. Okay, that's going to be important for us. A worker is standing outside on wet ground, okay? And the fact that it's wet ground tells us that there's no resistance for the earth. And so if he's standing on the ground, there's a very, very good conducting path there. He touches a 1,000 volt live wire, and he touches it with a wet hand, okay? And what that's telling us is this. We can assume that the skin resistance is very, very small under these circumstances. So, no resistance of the ground, no resistance of the skin. how much current are we going to get? Because it's ultimately the current that we're concerned about. And if we have a current that is 15 milliamps or more, then we could be in trouble. So we want to have a current less than 15 milliamps. That's what we're looking for. But we're going to solve for the current and see if that's true. Now, for starters, let's draw the circuit. And the way we'll do it is we're going to look at a circuit and we're going to use our basic model of the electric conduction in the human body. So here's our model for electric conduction in the human body. We've got certain resistances for the arms, for the torso, and for the legs. The worker reaches out and with one hand touches 1,000 volts. So one hand touches to a voltage of 1,000 volts. And he's standing on wet ground, but he's wearing boots that have resistance to protect him. And so those resistors are between him and the ground. And here's the earth ground here, which we'll label. Here's the big question. We need to know what is the resistance of the boots. And if we know that, we'll be able to compute the resistance for the entire conducting path. We know the voltage difference. If we know the resistance, we can calculate the current. But we've got to figure out the resistance of the boots. Well, we weren't told the resistance of the boots, but we were told the voltage and the current for a particular situation. At a voltage of 5 kilovolts, the most current that the boots will pass through the soles is 5 milliamps. Given that, we can deduce the resistance of the soles of the boots. And what is the approximate resistance for the soles of the boots? We'll give you some choices. Well, remember, our basic definition of resistance is just delta V divided by I. The potential difference is 5 kilovolts. We need to put that as 5.0 times 10 to the third volts. The current is 5.0 milliamps, which you need to write as 5.0 times 10 to the minus third amps. Calculating that out, we get a resistance of 1.0 times 10 to the sixth ohms, which is 1 mega ohm. So now we know the resistance of the boots. We can go back to our previous calculation and we can complete it. Okay, now we know the resistance of the boots, so let's go ahead and put that in. The resistance of each one of the boots is 1 mega ohm. Let's look at the current path. Okay, current comes from the 1,000 volts through one arm, through the torso, then it goes through each of the legs to the ground. But the current splits. Some of it will go through each leg. So this is what our current model looks like. And given that, we need to write down what is the approximate resistance of the current path. In order to figure out the current through the torso, we need to know the resistance of the current path. And what is that? Take a look at the diagram. We'll give you some choices. Figure out the approximate resistance of the current path that we're looking at. To make this easier to see, we're going to redraw the situation. Okay, it looks like this. I have 1,000 volts connected to the resistance of one arm, which is 310 ohms. Then we have the resistance of the torso, which is 30 ohms. Next, we have the resistance of the leg, 290 ohms, plus the resistance of the boot, which is 1 mega ohm. But we have the other leg as well, so we have 290 ohms for the leg and 1 mega ohm for the boot. And that is what's connected to ground. Now, if we look at the current path, we can see that there's two resistances that are so much bigger than everything else. The 1 mega ohm resistance for this boot and for this boot are bigger by more than a factor of 1,000 of all the other resistors in the problem. So if we're looking for an approximate value here, we can actually get rid of everything else in the problem. We don't have to worry about the resistance of the legs, or the resistance of the torso, or the resistance of the arms. The only resistor that makes any difference is the resistance of the boots. So the resistance of the current path is dominated by the resistance of the boots. So really, the situation looks like this. And let's look at the effective resistance for this circuit. Well, it's two 1.0 mega ohm resistors in parallel. Remember, effective resistance for resistors in parallel, 1 over R1 plus 1 over R2. R1 and R2 are both 1 mega ohm in this case. And if we calculate the effective resistance we get, it's this. It's 500,000 ohms. Now that makes sense because it's just 1/2 of the individual resistors. And that's a shortcut that we have. If we have two resistors that have the same value that are in parallel, the resistance is just 1/2 of either of them. So with that change, the circuit looks like this. I've got 1,000 volts, and between 1,000 volts and ground, I have a single resistance. Everything considered together, the body plus the boots, has a total resistance 500,000 ohms. So the current is equal to the potential difference divided by the resistance, 1,000 volts divided by 500,000 ohms. And so I get a current of 2.0 times 10 to the minus third amps, or 2.0 milliamps. And that is less than the threshold to cause any injury, which is good. But let's take a look at our result and see if this makes sense. So in the problem, we came up with a final answer of 2 milliamps. Now if we look at the table for values for safety, for working with electricity, for AC, the threshold for your sensation, where you can just feel it, is about 1 milliamp. So if you were in a situation like that, wearing the boots, worst case scenario, if you touch the wire, you'd feel it, but it's well below the threshold where it's going to cause you any physical problems. So you'll feel it, but you won't be injured. And that's probably a good thing. You'll know that you're touching a live electric wire, but it won't hurt you. And so you can take steps to rectify the situation. Now in my case, working in the studio here, if I turn on this electricity, my shoes have a resistance that's actually greater than what we saw in the problem, because I have very, very thick rubber soles. The thing is, they would possibly break down at really, really high voltages. So they're not intended for electrical safety. For this, the voltages are small enough, the resistance is high enough. 120 volts instead of 1,000 volts, higher resistance than we saw for the boots. So even though there's a 120 volt potential difference between my hand and the floor, there's not even a perceptible current. When I do this, I feel nothing. So I'll put my left hand back in my pocket, because it's a very different story. If I was to do this, then I would have a very, very different result. Again, don't try this, but it's illustrative to know that if you are going to work with electricity, you can take appropriate safety precautions, and they're designed so that you can be safe when you're working with it. And that's good. Physics is about the world, and we need to take steps to make sure that when we're working in the world, we're doing so safely.